All right, so we should get started now. Thank you for attending uh, this morning. This is the makeup class for the holiday that we took last week. Um, Today is Saturday. The date is 22nd of April. The year is 2023. Last time we talked about sampling of continuous time signals. Um, we proved that the effect of sampling is that the spectrum of the signal that we are sampling will be repeated. If XS is the spectrum of the sampling signal, the sampled signal, and X is the spectrum of the signal that we are trying to sample. Now suppose that the spectrum of X looks like this, where it is band limited. It has a maximum frequency of B. So B is the maximum frequency, and it is of course symmetric about the vertical axis. Um, so if we're sampling the signal X every Ts seconds, and the sampling rate is 1 over Ts, and the sampling frequency is 2 pi over Ts. The units of sampling frequency is of course radians per second. Now, the sample signal will have the spectrum that looks like this. So in other words, XS, which is the sample signal, will have a spectrum exactly at 0, which is the replicate of the spectrum of the sample signal. So it is repeated here, as well as other fractions of X. In effect, the spectrum of XS is just the spectrum of X put every omega s uh, radians per second. So it is like a copycat of X. So you're putting X, the spectrum of X, every omega s radians per second. So this is the spectrum of the sample signal. Now, if you notice here, the maximum frequency of X is B. So if we are looking at this spectrum, this part of the spectrum, then you see that of course the center of it is at omega s, as I told you earlier, and so this frequency will be B radians per second to the right of omega s. So it is at omega s plus B, and this point is of course at omega s minus B. Okay, so you see that if you look at omega xs here, the spectrums will not overlap as long as omega s minus b is greater than b. So it is this condition, and this condition suggests that as long as omega s is greater than 2b, twice the maximum frequency of the sample signal x, then the spectrums here will not overlap, and we will be able to retrieve the original spectrum of X back as long as they're not overlap. But if they overlap, okay, if the spectrums here are overlapped, then we will not be able to retrieve the original spectrum back for sure. So this will be the necessary condition, the critical condition for us to be able to retrieve the sample signal back. Okay, I'm sorry, for us to retrieve the original signal back from the sample signal by passing the sample signal through a low pass filter to extract only this part of the spectrum back, which we know is the spectrum of the original signal X. Okay, so that is uh, here. So under this assumption, we can get the original signal X back by filtering out all the side spectrums using an appropriate low pass filter. LPF stands for a low pass filter. Okay, in other words, we are trying to filter out all the unnecessary spectrums and retaining only the critical one, which is the spectrum of the original signal XS. So this is what it is here. Now, a couple of terms that you need to know are TS, which is a sampling period. It is the duration between the successive samples. And Fs is the sampling rate. The unit of Fs is samples per second. The unit here is samples per second. Samples per second. But the unit here, the omega s, is radians per second. That is due to the term 2 pi here, because 2 pi has the unit of radians. So omega s has the unit of radians per second. It is what we call the sampling frequency, and Fs is the sampling rate. So the sampling rate, so the Nyquist rate states that the Nyquist theorem states that we want the sampling rate, which is Fs, to be greater than the maximum frequency of the signal that we want to sample. This has unit of hertz of xt. Xt being the signal that we want to sample. Okay, so let me highlight it. Now let's look at an example. In this example, we have a signal Xs, which is composed of two sinusoidal signals. The first one being cosine 2 pi at frequency of 4,000 Hertz, and the other is another cosine at frequency 3,000 Hertz. Now, the first question is you want to find the Nyquist sampling rate of xt. Now, the Nyquist sampling rate is just twice the maximum frequency of the signal that we want to sample. Now, the maximum frequency, if you look at this expression, this expression has two frequencies. The first one is at 3,000 Hertz, and the second one is at 4,000 Hertz. So and of course 4,000 is greater than 3,000. So the maximum frequency of the signal is 4,000 Hertz. That's why the Nyquist sampling rate is just 2 times the maximum frequency. So it is 2 times 2 multiplied by 4,000, and that would be 8,000. Now you have to be careful. We are after the sampling rate, so the unit of this number 8,000 is going to be samples per second. Okay, samples per second. Basically, samples per second is corresponding to the unit of hertz here of the frequency. Now, in the second part, we would like to find out what happens if the sampling rate is 9,000 samples per second. Now, to find it, to do this one, first we need to plot the spectrum of the signal that we want to sample. In this case, it is x. So x here, if you look at this expression, as I said earlier, it's composed of two frequencies, one being at 4,000 and the other being at 3,000 Hertz. So that's why we have the 3,000 Hertz and the 4,000 Hertz. Now, they have to be careful though. the horizontal axis is angular frequency, and it has the unit of radians per second. So let me write that down, radians per second. But 3000 and 4000 are in hertz. So what we need to do is we need to multiply them by 2 pi to make them radians per second. So that's why we have 2 pi 3000 and 2 pi 4000 here. Okay, radians per second. Now this would be the original signal. The next step that we need to do is we need to draw copies of x. Okay, we need to draw copies of x every omega s radians per second. Now, again, you need to be careful. The number that you're given is in samples per second, but the unit here is radians per second. So we need to multiply this value by 2 pi before we can continue our process. So 9,000 multiplied by 2 pi would be 2 pi 9,000. So 2 pi 9,000 would need to be uh, 4,000. 9,000 should be about here. Okay, this is 2 pi 9,000 hertz, which is the sampling frequency. Okay, another one at the negative in the negative half. So this is minus 2 pi 9,000. Okay, and then we need to draw this. Okay, we need to put this here. Okay, but now instead of having the middle point at 0, we are positioning it here. So this point, the whole thing here will be shifted to the right by 2 pi 9,000. So this pulse will be at, let me write it down first, minus 2 pi 3000 here, minus 2 pi 4000. So this will have to be added by 9,000, and we would have 2 pi 5,000. So it is 2 pi 5,000 here. Okay, this is 2 pi 5,000. And this impulse will be at 2 pi 6,000 because we have to add 3,000 by 9,000 and we're going to get 6,000. So 2 pi 6,000 goes here. Okay, and this guy will be added by 9,000 to get 12,000. So 2 pi 12,000 will go here. And another one, 13,000. 2 pi 12,000. 2 pi 13,000. Okay, and as for this guy, right? As for this guy, we have to subtract everything here by 9,000. So starting with 4,000 subtracted by 9,000, we're gonna get negative 5,000. So negative 5,000 goes here. And this one subtracted by 9,000, we get negative 6,000. Negative 6,000. And so on. Okay, and so on. So now if you look at it here, okay, if you look here, you see that of course I think this is this one. The magnitude here is 1/2. So this would be 1/2 of TS. TS is 9,000. So 9,000, 45,000, 45,000. Now 45,000 comes from this. We have to have 1 over TS in the front. Okay, so but 1 over TS is just a sampling rate, right? Sampling rate is 9,000. So 9,000 divided by 2 is 45,000. 4,500, sorry. Now, if you look at XS here, which is the spectrum of the sample signal, we see that we can see the original spectrum right here without any distortion at all, without any disturbances. So there is no overlap. The green spectrums do not overlap inside the blue spectrum. So that's why we can use a low-pass filter to extract the blue impulses back. Okay, and once we do that, we're gonna get the original signal XS back. So in this case, the original signal XS can can theoretically be extracted. So no overlap. The original signal XT can be retrieved theoretically using a low-pass filter. Okay, by filtering out all the green impulses to get only the blue impulses, and we're going to get the original signal back. Now, let's look at part C. If you don't have questions, in part C, instead of sampling at the rate of 9,000, we now sample at the rate of 5,000. So in this case, the sampling rate is 5,000 samples per second. And since the maximum frequency of the signal is 4,000 hertz, right? And this implies that the Nyquist rate is twice, which is 8,000 hertz. So you see that right away in this case, the sampling rate is considerably less than the Nyquist rate. So in this case, the sampling rate is less than the Nyquist rate. So we cannot retrieve the original signal back from the sample signal. Therefore, we won't be able to retrieve Oh, retrieve the original signal back. Back from the sample signal. And the reason is this, okay? If you're trying to, first we have to draw the spectrum of the signal that we are about to sample. So this is the spectrum. Now we need to draw XS, all right, we need to look at the sampling rate, and we're gonna have to put this spectrum every 2 pi 5, so every 2 pi 1 10,000, 2 pi 10,000. No, 500. Every 2 pi 500. Okay, 5,000. Sorry, every 2 pi 5,000. So 2 pi 5,000 is here. This is 2 pi 5,000. This is minus 2 pi 5,000. So this is XS, the sampled spectrum, the spectrum of the sampled signal. Okay, so the spectrum of the original signal is here. So we need to put this every 2 pi 5,000, right? We need to put this every 2 pi 5,000. So the next one to do is this one and copy it right here. All right, so this is minus 2 pi 4,000. So let me write that down. Minus 2 pi 4,000. This is minus 2 pi 3,000. This is 2 pi 3,000. This is 2 pi 4,000. Okay, so we need to add 2 pi 5,000 to every one of these. Starting with this one, okay, added by 2 pi 5,000 will be right here, which is 2 pi 1,000. So this impulse, when shifted to the right by 2 pi 5,000, will be exactly here, which is 2 pi 1,000. And this guy, when shifted to the right by 2 pi 5,000, will be at 2 pi 2,000. And this guy will be at 2 pi 8,000 and 2 pi 9,000 respectively. So we have this one and this one. So 2 pi 8,000 and 2 pi 9,000 and so on. Okay. And as for this guy, all right, now we're looking at this position. We need to shift this to the left by 2 pi 5,000. So this guy will go to minus 2 pi 1,000. Okay. You subtract this number by 2 pi 5,000 and we're going to get negative 2 pi 1,000. So it is here. And the other one is negative 2 pi 2,000. So negative 2 pi 1,000, negative 2 pi 2,000. And of course, we have the one on the left as well. And those are um, 3,000 subtracted by 5,000. So this one goes to 2 pi, minus 2 pi 8,000 and 9,000 respectively. and so on. And if you look at this here, okay, if you look at this here, you see the original spectrum are at these impulses, right? Now, if you pass this, the whole thing through a low pass filter, if you try to extract the blue impulses back, right, you won't be able to get rid of these green impulses. So the green impulses will be a part of the signal that you are trying to filter out. Okay, so you won't be able to get rid of the green impulses. That's why in this case you won't be able to extract the original signal back, because you will always get this one with you. All right, this one, these impulses do not go away. So let me highlight it. This represent the original signal, and this represent the artifact from the adjacent uh, spectrum. Artifacts that cannot be that we cannot get rid of. So in this case, you see that from the diagram above, we cannot retrieve xt back from xs, okay, because there are some artifacts from the adjacent spectrum that results from uh, too low sampling rate. In other words, the sampling rate is not high enough, so we will not be able to get rid of this. So yeah, this hopefully this will clear up about how important the Nyquist rate is. So in conclusion, to be able to extract the original signal back, we need to sample the signal at least at twice the sampling, at least at twice the maximum frequency of the signal. Okay, we care only the maximum frequency of the signal, and that 2 times maximum frequency is called the sampling rate, the Nyquist sampling rate. Okay, right. All right. So right here we are done with sampling of continuous time signals. So if there are no questions, if you guys have any questions, please ask right away. But if you don't, I'm gonna have to move on to the next chapter, which is discrete time signals and systems. And that chapter is, I believe it's chapter number 7. So chapter 7. Discrete. Now we are turning our attention to discrete time signals and systems. We are moving pretty quick, so I hope you all catch up. So far we have been talking about only continuous time signals and systems. So far we've been talking about only about continuous time signals and systems. Signals. Okay, so what do we mean by continuous time? Continuous time signals are basically functions with the domain taken as a subset of real numbers. Okay, so these are just functions with domain with the set of real numbers as its domain. So in other words, the time can be taken as any number, okay, any real number. It can be an integer, it can be a rational number, an irrational number, it can be any irrational number, it can be floating numbers, okay. So for example, xt, right, the t here can be any number, any real number. Now in this chapter, we will be talking about discrete time signals. Now for discrete time dt, okay, for discrete time signals, their domain will be, instead of the set of real numbers, now the domain will be the set of integers, okay, the set of integers. And we will use the notation x and then a bracket n, okay, to stand for the value of the discrete time signal x at point n. Okay, so this is the value of a discrete time signal x at n, at time n. But now the value n here has to be an integer, okay? It cannot be a floating number. It cannot be any real number. It has to only be an integer. has to be an integer. Okay, so that means that we cannot talking about if we write this one, if we write it like as 1.2, then this is not correct, this is not correct, this is wrong. We cannot write it as like this, because the number, the value inside the bracket would have to be an integer. Okay, would have to be an integer. For example, x of -2, this is okay. X of 0 is okay. X of 1 is okay, right? These are all okay. These are okay because these are integers, right? These are okay. So now we're talking about discrete time signals where the index here would have to be integers. So let's do an example. Okay. Examples of discrete time signals, we have, let's say we are defining xs as 0.5 to the n, where n is 0, 1, 2, and so on, and 0 when n is negative. Everywhere else. And we can plot this signal, right? Let's plot this signal. And now to plot it, the horizontal axis would have to be n, okay? And we have to mark it as 0, 1, 2, 3, 4, 5, and so on. And this is -1, -2, -3, -4, and so on. And when n is negative, okay, x would be 0, so we'd have to put zeros here. And notice here, we do not consider somewhere between, right? We only consider the values of n. We only consider the whole value n here, okay? We do not consider any value in between. Now, when n is 0, n would be 1, so we draw 1 here, and then when n is 1, xn will be 0.5, so 0.5, well, actually it should be a little bit lower than that, 0.5 should be here, and half of 0.5 should be here, and half of it should be here, so approximately this. Now let's put some numbers there. This is 1, this is 0.5, this is 1/2, 1/4, 1/8, 1/16, 1/32. Now this is the signal xn. So this is an example of a discrete time signal. Okay, so examples of discrete time signals. The first one that I would like to talk about is called the unit sample signal. The unit sample signal. Now, the unit sample signal has the symbol delta. Okay, this is the unit sample signal, and it is defined as delta n equal to 1 when n is only exactly 0 and 1 point only, and it is 0 elsewhere. So if we try to plot this unit sample, we will end up with just this bar, which is exactly at n equal to 0, and everywhere else it would be 0. So we have this here, only at 0. Okay, this is 1. I'm sorry, this is 1. This is the plot of delta. So this is why it's called unit sample, right? It is one sample only that occurs at n equal to 0. Okay. And we know that for any uh, discrete time signal x n, we have if we multiply xn by delta n, the result will be x0. Okay, and delta n. You see that? It will be x0 delta n, because when n is other than 0, this one will be 0, right? This guy will be 0 when n is not equal to 0, and you know, the whole thing will be 0. But when n is 0, this guy will be 1. Okay, so that means that when we plug in n equal to 0 here, we will get x0 out, right? Because when n is 0, this guy is x0. But when n is not equal to 0, then this guy will be 0, and everything will disappear. And of course, we can shift delta. Okay, we can shift delta, and we'd have xn times delta n minus n0, and this is equal. N minus n0 will be 1 only when n is equal to n0. So first you have to notice that. And 0 elsewhere. So this guy would have to be equal to x of n0 times delta n minus n0, for the same reason as this one. So I'm not gonna talk about it again. So this is called the unit sample. The second example is called the unit step. The unit step. The unit step has the symbol un. Okay, un is the unit step, and it is defined as un equal to 1 when n is 0, 1, or 2, or 3, or 5, 4. In other words, positive integer, and it is equal to 0 when n is a negative integer. So we can plot the unit step discrete time signal u here: 0, 1, 2, 3, -1, -2. This is 1, and we have here 1, 1, 1, etc., etc., and then 0 here. So this is the unit step signal. Okay, discrete time unit step signal. The next one is exponential. We don't have a symbol for that. It is usually xn equal to a to the n un. Now, when we multiply any signal by un, it means that we are starting at from n equal to 0. Okay. Multiplication by un means we start the signal from n equal to 0. Okay. So if we are trying to plot this against n, okay, we will have this is 1, this is a to the second, this is a to the third, a to the fourth, a to the fifth, a to the sixth, and so on. And this is 0. Now this is the effect of multiplying by un. Okay, we have 0 when n is negative. All right, and then we have 1. Oh, sorry. This is 1. N is equal to 0, right? So a to the n would be 1. This is a to the second, a to the third, a to the fourth, and a to the fifth. And so on. So this is a, oh, by the way, this is for n, for a greater than 0 and less than 1. Okay, but if you have a less than 0, what would that be? If a is less than 0 but greater than -1, so we have this case. Now the xn will be positive and negative depending on a. If a is an even number, xn will be positive, and but if n is even, then xn will be positive, but if n is odd, then xn will be negative. So we have this. Okay, when n is 0, when n is 1, when n is 2, when n is 3, when n is 4, 5, and so on. This is a, this is, first one is 0, I'm sorry, first one is 1, which is a to the 0, and it is 1. I should write it down like this. This is a, this is a, squared, a cubed, a to the third, a to the fourth, a to the third, a to the fourth, a to the fifth, and so on. This is when a is less than 0. You have a to the n positive and negative numbers alternately. Okay. All right. Okay. Now the next one is about the energy of discrete time signals. I'm going to be using the letters dt to stand for discrete time to save some time for convenience. Okay, given a discrete time signal xn, its energy is defined as Ex. Now the subscript x will tell you that it is the energy of a signal x. If you have a signal called y, then you're going to have E sub y. If you have a signal called z, then you're going to have E sub z. But now we are supposing that the signal is called x, so we have E sub x. So the energy E sub x is defined as the summation that goes from minus infinity to infinity, and then the magnitude of the signal x squared. Okay, this is the definition of energy. Okay, the magnitude here is important when x is a complex number. Okay, the magnitude signs, the magnitude signs are important when xn is a complex number. In other words, if you are dealing with a complex number signal, then when you want to find the energy, you'd have to use only the magnitude value of it. All right, so you have to have the magnitude symbols. You don't want to throw it away. If you throw them away, then you'd have trouble. Okay, so example. Okay, let the discrete time signal xn be defined as xn equal to minus 2 times let's say 0.5 to the n, where n starts from 0, 1, 2, 3 until 10. Okay, I'm sorry, until 3, 1, 2, 3, and then 1 when n is 4, not 1, sorry, minus 2 when n is 4, 5, and then 0 else. Now let's try to find the energy of this signal. So by definition, the energy of X is summation that goes from minus infinity to infinity, the magnitude value of X squared. Okay, so we have the first four terms are from n equal to 0 to 3. Okay, so we have 0.5, when n is 0, right? 0.5 to the 0 squared plus 0.5 to the first squared plus 0.5 to the second squared plus 0.5 to the third squared. Now these are for n equal to 0 to 3. Now the second part is for n equal to 4 and 5. So plus minus 2 squared plus minus 2 squared. Now this is n equal to 4 and then n equal to 5. And that's it. We don't have anything else because when n is something else, xn would be 0 and we don't want to write it down. So this is 1, right? So it is 1 plus 0.5 squared plus 0.5 squared plus 0.5 to the fourth plus 0.5 to the sixth plus 4 plus 4. Okay, and we have 1 plus 1 half. No, not 1 half. 1 plus 1 fourth plus 1/16 plus 1 2. No, not this is 6. This is 6. 30, 62, 64, and plus 8. Okay. So this is divided by 64, 1 plus 4 plus 16 plus 64 plus 8. And that is, I'm gonna have to use my calculator. Where's my calculator? Did I forget somewhere? Not here. Here's my calculator. We have 5. 85 plus 64 times 8 divided by 64. So we have 9, 597 over 64 units squared. Okay, divided by 64. About 9 point something. Okay. Right. Now let's look at another example to find the energy. The energy of un, which is the unit step, is infinity, because summation goes from minus infinity to infinity. Un squared is just summation. N goes from 0 to infinity, 1, right? And that would be infinity. Okay, let's look at another one. Let xn equal to a to the n un. Okay, where the magnitude of a is less than 1, then the energy of x would be summation that goes from 0 to infinity, a to the n, right? Squared. Okay, and that is summation that goes from 0 to infinity, a squared to the n. Okay, I just interchanged 2 and n, right? 2 and n are interchanged, switched, so we got a to the second to the n. Now, this is 1 plus a squared plus a to the fourth plus a to the sixth plus a to the eighth plus blah blah blah. And you notice right away that this is a geometric sum, geometric series. And if you notice, if you remember, if we have r to the n, where n goes from 0 to big N, then this is called a geometric sum, and the sum will be equal to 1 minus r to the big N plus 1 divided by 1 minus r, okay, where r is not equal to 1. Now, if we have infinite terms, okay, now when the big N converges to infinity, we're going to have 1 over 1 minus r, given that the magnitude of r is less than 1. So this is geometric sum. You should have seen this when you were in high school, so I'm not going to repeat it. And you notice right away that this is a geometric sum, right? And so this is equal to 1 over 1 minus well, actually, sorry, this has to be absolute a. I forgot the absolute symbols. Sorry about that. So 1 over 1 minus absolute a squared, when absolute a is from 0 to 1. Okay, so this is the energy of this signal. Now we have to talk about operations on discrete time signals. The first operation is time shift. the time shift operation is x bracket n minus n0. Okay, so whenever you see this, means that we are shifting the signal x to the right by n0. So if n0 is positive, then we're shifting xn to the right. But if n0 is negative, means that we're shifting x to the left. So n0 is positive, shift right. But if n0 is negative, shift left. Okay, for example, u of n minus 2 would have to have the graph that looks like we're shifting u to the right by 2 samples. So we're gonna have 0, 0, 0, 0, and then 1, 1, 1, right? It has to start from 2, 3, and 4. But if we have u n plus 2, then we are shifting u to the left by 2 units, by 2 samples. Right, we have this, we have this, we have this, we have this, and we think I should move it here, right? And then I should change this to 0, oh, sorry, 0, 1, 2, minus 1, minus 2, and then minus 3, minus 4 are all 0. Okay, and of course, the height will be 1. So we are shifting right or left. Now this is the time shift. Of course, you can do it algebraically by plugging in n equal to n minus 2 or n plus 2 into the expression, mathematical expression of the signal that you are considering. So let me do that. un plus 2 is equal to 1, 0, n plus 2 equal to 0, 1, 2. So this is equal to 1 when n is minus 1, minus 2, minus 1, 0, 1, 2. This is algebraic approach. Okay. The next operation is called time reversal. Time reversal is easy. Okay, you just rotate the signal around by 180 degrees, around time 0 by 180 degrees. Time reversal is x of minus n. This is time reversal. This is time shift. So in effect, we are rotating xn around n equals to 0 by 180 degrees. So left to the right and right to the left. Okay, we are rotating left to the right, and we're rotating right to the left. So if I am to, for example, u of minus n would be 1 when minus n is 0, 1, 2, 3, right? So this is equal to 1 when n is 0, minus 1, minus 2, and so on. So if we want to plot it, then u of minus n would be this. You see, we are rotating it around by 180 degrees. Okay. Here. Now, what about u of minus n plus 2? So how should we draw this? u of minus n plus 2 has to be equal to 1 when minus n plus 2 is equal to 0, 1, 2, and so on, and 0 else, right? We're trying to make sense of it algebraically. So this is equal to 1 when n is equal to uh, 2, 1, 0, minus 1, minus 2, and so on. So if we plot it, we'd have 0, 1, 2, and then 0, 0, minus 1, minus 2, minus 3, minus 4, and so on. Okay, we have 1, 2, 3, 4. This is so on. Minus 1, minus 2, minus 3, minus 4, of course 1. Okay. This really makes sense algebraically, but if we really want to, if we don't want to use algebraic approach, we can determine the graph of u of minus n plus 2 here. Or we could write u of minus n plus 2 as u of minus n plus 2 equal to u of minus n minus 2. Okay. And so we see that looking at here, we can see that it is actually n minus 2, and then reverse it. Now let me take a look. N minus 2, and then reverse it. No, n minus 2. And then flip it. Doesn't make sense. N minus 2. N minus n plus 2. 0, 0. Okay, I see it. So this means that we will have to first reverse it, reverse UN, and then shift the reversal to the right by 2 units. Okay, and so the first operation, in the first operation, we are reversing it. We are reversing U, right? So this is the first step, reversing U. So this is U of minus N. And then we shift it to the right by 2 units. Minus N plus 2. So we have shifted 2 units to the right. So we have this. Okay. Here. This is reversed. UN. And then shift reversal. Shift the reversal to the right by 2 units. Here. Okay. So in general, if we want to plot x of minus n plus what? Plus k, then we do 2 steps. Okay. First, we rotate. We do time reversal on xn to get x of minus n. Okay. So we plot the time reversal x of minus n, and then from the plot shift it to the right if k is positive, and the left if k is negative. Shift the reversal to the right if k is positive, and the left is when k is negative. For example, here, this is k is positive 2, right? K is greater than 2, so we shift this thing to the right 2 time units. But if we, instead of minus n plus 2, if we had u of minus n minus 2 here, then we would need to shift this guy to the left 2 time units because of k being negative. Okay. Now the third operation that we could do on discrete time signals is a time scaling. Time scaling, time scaling. Okay. Time scaling is yn equal to x of an. So this is called time scaling, x of an. Actually, I don't need y. Now, time scaling is a little bit tricky because you need to be careful about what you need to be careful because if you remember, the value inside the brackets must be an integer. So whatever you do, you can have this one as an integer. When a is less than 0, this is okay. But when a is greater than when a is less than 1, then this is not difficult. But when a is greater than 1, then you'd have to be careful. So let me write it down for you. If absolute a is greater than 1, then we are actually compressing x by a factor of absolute a. Compression. But if a is less than 1, then we are kind of like stretching it. Laterally. To the side. Now, let's look at an example to see what I meant. Let xn be 0.5 to the n exponential, right? 0.5 to the n un. Then and let y1 be x of 2, let's say 3n. Okay, and y2 be x of n over 3. Now let's try to plot this. Okay, let's start with y1. y1 is x of 3n. So you see, I'm gonna draw a line here. I'm gonna draw a line here, and then I'm gonna do y1 on the left, and I'm gonna do y1 on the right. So when is 1? When n is 1, right? When n is 1, y1, I'm sorry. When n is negative, when n is less than 0, y1, yn would be 0. This is obvious because whenever you plug in n equal to a negative number, you're going to get n at a negative number, and that would be 0 by the effective view. But when n is 0, you have y1 of 0 equal to 0. I'm sorry, equal to 1. Actually, I should write 0.5 to the 0, and that is 1. When n is 1, I have y1 equal to x of 3, right? This x is 0. When n is 2, we have y1. Oh, sorry. this is 1, this is 2, equal x of 6. Okay, when n is 3, you have y1 at 3 equal to x of 9, and so on. So you see, if I plot x of n, so this is x of n, this is x of n. Now y1 would be 0, 1, 2, 3, 4. This is x of n. This is y1 of n. So when n is less than 0, of course, we're going to get 0 and 0. But when n is 0, we're going to get x of 0. Okay. But when n is 1, we're going to get this one will be here. This is when n is 1. Because we get what? X3, right? We got x3. y1 at 1 equal to x3. So x3 will be right here. Okay. When n is 2, y1 at 2 is equal to x6. So x6 would be here, right? And so on. So this is x0, x3, x6, and x9. So you see that only these values of x are eligible to be values of y1. Okay, these are the green ones are eligible, whereas the pink ones will be thrown away. Okay, the green ones are only the green ones are eligible. Whereas the pink ones are thrown away. I should use some other colors. Let's see. Let's use blue. So this is the effect of the fact that n has to be integers only. Okay. Now, so y1. So if you are shrinking, if you're compressing a discrete time signal, then you need to be careful because some of the samples will be lost. For example, here, okay, you cannot divide 1 by 3 and get an integer, right? Because 1 over 3 is not an integer, so this one is lost. Same goes here. If you divide 2 by 3, you're not gonna get an integer, so this one is lost. But if you have 3 over 3, then you're gonna get a 1, so this one is eligible and it goes here. Okay, right. Now let's look at this one. Again, when n is negative, y2 would be 0. When n is 0, y2 would be x of 0. Okay, when n is 1, y2 will be x of 1 over 3. So this is not eligible, right? We don't have a value for this one, so we just write it down as 0. Okay, when n is 2, y2 at 2 is x of 2/3. Again, this is not eligible because the parentheses, the bracket, the values inside the bracket has to be an integer. So this one is 0. But when n is 3, y2 at 3, now we're talking because this is going to be 1. And that is x1. So this is eligible. So if you're trying to plot this, so we have xn first, xn, x0, x1, x2, x3, x4, and 0, 0. Okay, this is 1, 2, 3, 4, minus 1, minus 2. And now I'm plotting y2. y2 of n, of course, y2 is 0 is x0. And when n is negative, like this. Now, at y2 at 1, y2 at 1 is x is 0, y2 at 2 is 0, but y2 at 3 is 1. So we have 0, 0, and then this, and then 0, 0, and so on. 0, minus 1, minus 2, 2, 3, 4, 5. So this is x0. Oops. This is x0, x3, and so on. Oh, sorry, not x3, x1, x1. Okay, so we are actually, this one stays the same, but we are expanding x by a factor of 3. So this sample will be expanded to be at this position. Okay, so from 1, it is relocated to 3. Okay, and this guy as well, from 2 has to be relocated to 6, and so on, right? So we are, this case, y2, we are expanding x, but for y1, we are compressing it. But to compress it, it's like we are having a bin at every end, right? If the signal here doesn't go inside a bin, then it is thrown away. It has to be inside the bin. So this one has to be inside bin 1. Okay, at 6 has to be inside bin 2. But here, in this case, we have a bin here. 0 will go here, but 1 will go here, and 2 will go here. For these locations, we don't have associated x with it, so this one will be 0. Okay, so we are expanding. This one will be compressing. Last operation. Okay, if you have questions, you can ask anytime. The last operation is called amplitude transformation. We are almost done. The amplitude transformation looks like this. We have alpha xn plus beta. This is an amplitude transformation. Okay, alpha is the vertical scaling. Beta is the vertical shift. Alpha is vertical scale. Vertical scaling factor. Okay, and beta is the vertical shift. The amplitude transformation, everything we do in the amplitude transformation, we are doing it on the value of x. Okay, but everything we do in the time scaling, time shift, time reversal, we do it on the position of x. The time operation on the time doesn't change the value of x, but it is just relocating the location of each sample. But for the amplitude transformation, we're not messing with the relocation, but we are only doing it on the value of x. Okay, we're taking the value of x and we transform it, but locations will be the same. Okay, but the time transformation, as for the time transformation, the the magnitude will be the same, except that the locations will be transformed, will be changed. For example, uh, example, let yn equal uh, to u of n minus 1. So what we do is we multiply the value of un by 2. So this will give us 2, right? Starting from n equal to 0 on, and then we subtract it by 1. So the result will be just u, right? This is going to be u. This will come out as u, okay? Right. And this is y1. What about y2? N minus u minus 2un plus 1. So what is this? This is just minus un. Okay, all right. Amplitude transformation is easy. Okay, I think I should stop now, and I'll see you again on Tuesday in class. You guys have any questions? You guys who are attending, do you have any questions? All right, so if you don't have any questions, I'll see you in class on Tuesday on site. Bye bye, have a good weekend.